Hello, in this video I'm going to round off this section on the structure of matter by saying a few words about chemistry. I'm not going to say a lot because first of all I'm not a chemist, and secondly I'm not doing a series of videos on chemistry, but I think it's a good idea to take a closer look at chemistry as a subject and just see how it fits in with physics, I mean both now and in the past, because there's certainly a lot of overlap and there's no way you can draw a solid line around chemistry or physics and say, right, this is one subject contained and this is the other one. There's always going to be grey areas. So if we think about what we've looked at so far, we've looked first of all at classical mechanics, which is our big macroscopic objects moving around in space and time. So we've looked at all of that. We've then, in this section, we've gone to the small extreme of looking at atoms and nuclei and such like, and we've sort of left this gap in the middle, and a lot of this gap that we've got is filled by chemistry. So we were concerned with the macroscopic here in physics. We were concerned mainly with the subatomic here because we were looking at fundamental particles and binding energy and things like that. So you've got this bit in between the microscopic, and this is going to be really the foundation of our next topic when we move into thermodynamics, that this is where you're getting the most overlap between physics and chemistry. So the first thing is the binding of these atoms together, which is to do with descriptions of the electrons. As you'll know from even basic study of chemistry, it's these electrons in the atoms that then get shared essentially between atoms, which is what's holding these electrons, these atoms together into molecules and lattices and crystals and things like this. So the focus on electrons is a chemistry thing. We're less interested in that maybe in physics. I mean, we are interested in electrons because they come up in a lot of places, but not in terms of the binding of atoms together into molecules. That's very much a chemistry area. In physics, we're concerned with how electrons behave, and such as electricity and things like that. That's all based around electrons, or a lot of it is, the most of it is. So yeah, we have a different approach to what's going on with electrons and a different concern there. I mean, we can describe now all of this stuff in chemistry can be described by quantum mechanics. So theoretical chemistry is explained by quantum mechanics. So from that point of view, if you really go down into the depths of chemistry, then you're moving into physics. But that doesn't mean to say that you can just replace chemistry with quantum mechanics, because that detailed quantum mechanical description of what goes on in chemistry isn't necessarily the best description in all cases. It's still better to describe and easier to understand reactions and molecules and such like by using the traditional methods of chemistry and the traditional descriptions of chemistry than it is to describe everything in quantum mechanics. There's this sort of emergent complexity that's going on, that if you try to explain everything that's happening in every chemical reaction in terms of quantum mechanics, in terms of physics, you're going to just end up in a complete mess. So yeah, you've got this emergent complexity that needs to, or is most easily described at a higher level of analysis. So this is another thing that we're going to see. Well, actually, you compare this a bit to classical mechanics. We're looking at attributes and properties at the macroscopic level of material, and then describing the physics of that object in terms of those macroscopic properties. We're going to have this in the next topic when we start looking at thermodynamics. And this brings on another area of overlap with chemistry. So in thermodynamics, do you follow the route of classical thermodynamics, where you're describing amounts of substance in terms of temperature and pressure and volume, things like that? Or are we describing it as massive collections of particles? So which one are we doing? Are we looking at the individual particle level, or are we looking at it as the aggregated level? And you could make a similar case here of this distinction between quantum chemistry and traditional chemistry. So we've got that. There's also a big overlap here in thermodynamics. So actually, with this bit of looking at individual particles, that this brings us into the realm of modern physics with statistical mechanics, where you're then using statistical methods in order to describe probabilities of certain things happening in large amounts of particles. So whether it's to do with particles in a gas and how they're behaving, or whether it's particles in a reacting substance, what's happening, what's the rate of reaction, how many particles are going to be reacting. These are things that we can deal with statistically using statistical mechanics. So we've got another big overlap there between chemistry and physics. Now, earlier on, in the early days of chemistry, there was huge crossover in other areas as well. I mean, all of this atomic theory that was put together in the early days of classical science, so just after the scientific revolution, and they're trying to work out, well, what's an atom, what are atoms made of, what are all of these different materials made of, why is iron different to water, and all this sort of stuff. All of the groundwork really for atomic theory came from chemical experiments, and we're going to see a lot of that coming up again in thermodynamics. The work of people like Avogadro, who, of course, Avogadro's constant, number of particles in a mole of a substance. These numbers and the Avogadro's law about how you can have these integer quantities, these ratios, they're always ratios, integer ratios of reactants in these chemical reactions. This is the sort of information that was feeding into atomic structure, because it was allowing the periodic table to be built up, and then you're getting a more detailed understanding of the differences between these atoms. So early atomic theory was primarily chemistry. You'd now say that atomic theory would now be primarily physics, because they've taken over. It's more the concern of physics, the whole zoo of fundamental particles, whereas chemistry is much more focused, as we've said before, on the electrons. So, yeah, the relationship between physics and chemistry can change historically. So, but yeah, we've definitely got that big overlap of what's going on at the microscopic level and this statistical mechanics. Chemistry is going to be guided more, maybe, particularly when you get into organic chemistry. Also, we're moving into biological matter. So the types of matter which is of most interest is going to be guided by the stuff that's in the world around us. So, yeah, there's going to be more time looking at this carbon-based organic matter. And that, of course, is then going to feed into biochemistry and then into biology itself. So you can start getting into more of maybe a historical element to chemistry if you move towards that biological end. Of course, one of the things in physics that physicists like to focus on with this is the laws of physics haven't changed over time. These are laws that apply everywhere in the universe at all times. We're trying to look at the most fundamental level. There is no historical element to this. There's no, and back in the past this is how the universe behaved and now it's behaving like this. The laws are meant to be, at least we know at the moment, constant over time. For most of chemistry you're going to be saying much the same thing. These electrons aren't behaving in different ways, but the focus of chemistry at the biological end is going to be influenced by this, because of course biology has got a significant historical element in it. You start looking at things like evolution and such like. Well, what is considered to be the fittest, if you're having survival of the fittest, is going to be contextual, and then it's got that change over time. So you're talking about changes through time of how things are behaving. So chemistry can start touching at that, the bottom end of that historical sweep that you can have on a subject. So Yeah, I think really the takeaways from this are there's still a lot of overlap, particularly things like statistical mechanics and in this microscopic realm where there are grey areas between what is physics and what is chemistry. In the past, there was more overlap because of things like atomic theory coming out of chemistry into physics and then physics mainly taking it over. But there's a definite difference of emphasis that chemistry is more about the electrons, whereas physics is trying to describe all of the fundamental particles, unless we're looking at these macroscopic objects, in which case, yeah, we're looking at a higher level, we're abstracting up to look at a higher level of how things might behave and move around. So that's just a brief overview of certain things. It's interesting to think about. I'd recommend looking at, it's quite early on in the Feynman lectures in volume 1. He does a description where he compares physics to each of the other sciences. So he goes through chemistry, biology, I think astronomy, maybe even geology as well. I think that might be in there. It's not that long, it's only a few pages, and it is quite an easy read. It's got the usual Feynman's flair, and yeah, it's just easy to get to grips with it, really. There's no equations or anything in there. It's just a little descriptive passage. So I'd recommend going off and finding that. It's all freely available online if you just Google the Feynman lectures. And it's in that first volume. I think it might be chapter 2 or 3 or something like that, after he set out his initial stall. So maybe go away and have a read through that. But I just wanted to include this in the structure of matter section because it is one of the key areas where we do have that big overlap and that grey area between physics and chemistry. So it seems right to mention it now.